Yes, hello friends. So this is the video tutorial for today's GFG problem that elements in range A to B. So this is a medium problem, but I think it is one of the easier medium problems. So the question is pretty simple. It says given an unsorted array ARR and 2D array queries of size Q, where each query is of the form A to B. For each query, count how many elements in the array lie within the range A to B. So here, let's say for this query 1 to 4, how many elements are between 1 to 4? We can see this 1 is between 1 to 4, this 4 is between 1 to 4, this 2 is also between 1 to 4. So the number of elements is 3. For 3 to 6, again, this 4 and this 5 satisfy that they are between 3 to 6. So the answer is 2. For 0 to 10, all of these elements are between 0 to 10. So the answer is 5. So the final answer will need to create a vector of this, which is basically the first element is the answer of the first query, the second is answer of second query, and so on, and then we'll return this. Okay, so yeah, how can we solve this? See, one way is that obviously that we can brute force this. What I mean by brute forcing is that for, let's say, for a query between A to B, so the query is that we need to find the number of integers between A to B. We can traverse the array, and we can maintain a counter variable here. For each value that is between A to B, we can do counter plus plus, and then finally return our counter, and we can say that the answer of this query is this counter, right? So that is one way that you can do, but the problem in that way is, see, what would be our time complexity for each query? Okay, why is this not getting erased? Okay, that's fine. For each query, how much work are you doing? We are traversing the whole array, so we are doing n work. Okay, so for each query we are doing n work, and the number of queries we have is q. So our total time would be n into q, and we can see at the constraints here. So okay, sorry. Yeah, we can see the constraints here is that n and q are both less than 10 raised to the power 5. So if that is the case, then this would be 10 raised to the power 10, and this would TLE, right? So if we cannot do this, what we can do? So you are given that the array is unsorted, but can we sort it? Obviously you can sort it. So let's sort it. 1, 2, 4, 5, 8. This becomes a sorted array. What is the benefit of sorting the array? Is obviously we can use binary search on this, right? Okay. We can use binary search on this, but how is that beneficial to us? See, if I tell you that, let's say, let's not deal with the range A to B. Let's deal with this range. So A to infinity. That is, we want the number of elements in this array that are greater than A only. So if I just want this, you will also tell me that, okay, the linear way is not the best optimal, because I know an algorithm known as binary search on sorted arrays. So I can use binary search on this array, and then I can find the first element that is greater than A. So let's say I want the number of values that are greater than 10. So that is in this range, 10 to infinity, right? Or 10 is not a good value to use. So let's say 3. Number of values that is greater than 3, right? So what you will do, you will do binary search on this. You will find the first index that is greater than 3, right? So let's call this index as I. Okay. And then can you say that all the values that are occurring after I would also be greater than 3? Yes, because this is sorted. So the number of indexes that is greater than I would be n minus I, right? So here it is 0, 1, 2, 3, 4, n is 3, so 5 minus 2 is 3, right? So there we have three indexes that are greater than I. Okay, that makes sense. Now, if I ask you the inverse of this problem, so inverse of this problem is, I want the number of values that are in this range minus infinity to 5. So again, you will do binary search on the array. You will find the first index that is less than 5, right? Because we want all the values that are less than 5. So you will find the first value that is less than equals to 5. Let's call this index j. Let's call this index j. And then you will tell me that all of the values that are less than j, or after all the indexes that are before j will have this value greater than less than 5 only, because again this is sorted. So the number of values then you will tell me is j plus 1, right? Now, if you know this index I, if you know this index j for a and b, so what I'm saying is, let's first do a binary search, and let's first find this index I, that is the first value that is greater than a. Let's also find the second, also find the first index that is less than equals to b, and let's call this index j. So can I not say that for my range between 3 to 5, if I know this index I, if I know this index j, all the values that are in between this j minus I plus 1, right? Because both of these are valid. So all of these indexes that are in this range will actually be in the range 3 to 5, which makes sense because all the values after I are greater than 3, and all the values before j are less than 5. So all of the values between them would be between 3 to 5. So the answer for this query would be j minus I plus 1. Now, how is this better? See, before we were doing n time n amount of computation per test per query. Now we are just doing login because we are doing two traversals. You can say two login, but that is like the time complexity of this is login only, right? So now our computation becomes q login, and this is fine, right? Because see, this is 10 is to the power 5, and log of 10 is to the power 5 would be around 20. So this would be 2 into 10 is to the power 6, right? Which is fine. Okay. Now one thing that I want to say is that in my implementation, I did not implement my binary search. I use my lower bound and upper bound functions, which are inbuilt C++ function. So if you do not know what these functions do, let me just tell you. So in the lower bound function, if you do lower bound of x, and let's say you also do upper bound on x, lower bound of x would give me the index, or not index exactly, but it will give me an iterator of the first index, or the first element in the array, which is greater than x. Again, lower bound, upper bound basically do binary search in itself, but they are a wrapper on binary search, so you do not have to implement it. So lower bound will give me the first element that is greater than or equals to x, and upper bound will give me the first element that is greater than x. So this is greater than or equals to, this is strictly greater than x. So if I do lower bound on a and upper bound on b, let's say this gives me one iterator lb, this gives me another iterator ub. So what would our answer be? Our answer be ub minus lb, because see, if always remember, if you are dealing with a range L to R, and both of these elements are in the range, so this is the case that L is also included in the range, R is also included on the range. So the number of values is R minus L plus 1, right? This is what we was taught in school. And if we are doing this, so L to R, but one of these are not in the range, so it could be L to R. You can prove this also using like AP, because here this is nothing but an arithmetic progression which has the first element as L, the last element as R, and the number and the D, or the uh, yeah, D equals to 1, because all of these elements are plus 1 plus 1 plus 1. So if this, and you can find the number of elements if you want to prove this result also, but yeah, this is a result you should remember, and this makes very much sense also. So if this is the case that only one of them are included, the number of values are R minus L, right? We can also, like, if we, let's say we have this case, so 2 4, so the number of values that would be in the range is 2 to 3, right? Because 4 is not included. This is the case. So 4 minus 2 is number of total values. Yeah. So if you know the upper bound, you know the lower bound. So the number of values in between them would be ub minus lb. So because ub is not included, right? Because ub is the value which is greater than b. So let me show you the code. I think it will help you understand. So I sort my array, as we have to do binary search on it. I go over I also create my answer, which is of the QSI, number of queries basically. Then I go over all the queries. I calculate my, okay, so I'm changing X as A as X and Y as B. So I call this get count function, which will get the count of number of values between X and Y. So how I get this is basically I get the upper bound on Y. So the first value that is greater than Y, I get the lower bound on X. So the first value greater than equals to X. And see, all the values that are before the upper bound will be in the range, because this will give me the first value that is greater than Y. So all the values before it has to be less than equal to Y, right? So UB will not be in the range, but so this is how we will use this result, right? We saw here that L, if L is in the range and R is not in the range, number of values are R minus L. And similarly here, LB will be in the range, but UB will not be in the range. So the number of values between them would be UB minus LB. So this will give me the answer for one query, and we are calling this for all the queries. So we can submit this. The time complexity here is Q log n, and the space complexity here is O of n, because we are creating this answers variable. Why the fuck is this giving TLE? Okay, give me 1 second. Okay, typical GFG stuff. I do not know why this was giving TLE. Now it's getting submitted. don't trust on GFG compilers and GFG test cases. That is my like thing that you should remember. Like you see here, so I submitted this last night. This got corrected. Now it's giving randomly DLE. Then it's getting submitted again. Don't trust on GFG compilers. They do give good questions, like very typical DSA questions, but their compilers and their test cases are very weird. So that's fine. Yeah, if you were able to understand anything, or give me a like and subscribe, all of those things. I don't like to beg, but bye.